Yes, class. Am I audible to all of you? Deborah, Fadil, Pia.
Yes, ma'am.
All right. So in the last class, we had started with electric potential. Now let us quickly complete the equipotential surface. That's why I started this class earlier also today. So at least duration. And yesterday there was a lot of confusion between whether we do have the class or not. Right? Because some revision tests were also there yesterday. Then revision tests were also cancelled. Some students had their exam also. All right.
Yes, ma'am.
Okay. Now let us start with equipotential surface. This is a very easy topic, very easy to score, but an important topic that comes in the exam. But it's very easy. We'll complete it in one go. You just have to remember the properties. That's it. If it is used in numericals, you should be able to identify what is equipotential surface. It's not difficult. Equi means what? Equal. Potential, you already know. So equal potential surface means a surface which has equal potential all the time. So VA is equal to VB is equal to VC, which is equal to 2 volt. Suppose this is a surface. So at every point I'm taking it as 2 volt. So this becomes an equipotential surface. Suppose this is a random surface. It need not be a sphere properly. It need not be a circle or a symmetrical figure. It's a rough figure, random figure. So V at A point is equal to V at C point is equal to V at E point. If this condition is valid, means at every point you're getting the same potential. You can just name this directly as an equipotential surface. All right. So wherever you see the potential is same. So yes, potential and every point. Now coming to the properties, please pay attention and understand this in one. Potential at every point on equipotential surface is same, right? This is the first property. That is, if you choose a surface, you take this point, A point, some value is existing, let's say 2 volt. You choose another point, B point. At this also 2 volt is there. Any point you take, you have 2 volt. So VA is equal to VB. If this is valid, then your surface is an equipotential surface. Remember, we did this formula, work done is equal to charge multiplied by change in potential. Right? Charge multiplied by change in potential. So see, if there isn't any change in potential from one point to another point, if your potential is constant, so will there be any change? No changes in potential. Right? If voltage is constant, change in potential is 0. Right? If there is no change in potential, then work done is 0. So always remember, this comes a lot in your very small marker questions, and many students waste their time in calculation and analysis. Why? What should be the work done of equipotential surface? No value of charge is given, no value of potential is given. How do we calculate the work? Then we don't have force, we don't have displacement, nothing. Work done on an equipotential surface is 0. This should be at your tips, all of you. Any day I'll ask you, because this will be used. Work done will be 0. Logic is also very easy. If something is constant, something is not changing, its change is 0. So work done will also be 0. Now the third point is electric field. Whenever, if I tell you this is an equipotential surface, then whenever you draw an electric field, we draw no electric field lines are present, then tangentially we draw. We have all done this. Directly nothing here. Just draw the electric field perpendicular to the surface. Any point you take, electric field will be perpendicular to the surface. All right. Next, we have regarding the strength of electric. See, when equipotential surfaces are closer, that depicts the electric field is stronger in that region. And when the electric equipotential surfaces are far apart, right, they are at a distance to each other, that shows the electric field's magnitude is low. Suppose I give you this 1, 2, and 3. Then you can directly figure it out that electric field in this region is stronger than electric field in the second region. There's a reason to it that we have a formula E is equal to minus dV over dr. So electric field is inversely proportional to distance and all. That we'll do it today later. But right now, just regarding the equipotential surfaces, focus on its properties. That is, the equipotential surface for stronger electric field are closer, and for weaker it is depicting that they are located at a distance to each other. Now, when it comes to draw an isolated point charge, So you will be drawing isolated point charge. You are given and you have to draw equipotential surfaces. Equipotential surfaces you have to draw. Okay, so isolated point charge is there. Plus Q is present. So you will be drawing these charges like this. The equipotential surfaces around the charge. This is just fixed. So we represent it through the form of circles. All right. So you just have to remember how to draw two charges. This is how we draw it. These are the equipotential surfaces. Means these are the surfaces having same potential at every point. At this point, at this point, at this point, it is the same. But it's just a depiction. So this is not a tricky question that you have to apply your mind. No, you just have to remember it. This is it. This is the standardized figure, how to draw isolated point charge for an equipotential surface. If you have two positive charges, then see, here what will happen? Electric field for positive will be towards one side, electric field for this will be on other side. So it means they are electric field are in opposite direction, right? This will be E1, this will be E2, they are in opposite direction, right? So it means electric field is less, so there is a lot of distance. Here electric field is stronger, so lesser distance. Same way if you draw negative charges, same will occur for negative charges also. Here it will be closer, here there will be a distance. Closer, here a distance. There closer, here a distance like this. Same thing for negative also, because the logic is same. For electric field, for negative will point towards this, for this negative will point. Again, it will be, it's just that E1 will be this time, even E2 will be this time, but resultant will be less. But when you're drawing a dipole, both are attracting each other, right? This is attracting this is attracting this. Electric fields are in the same direction. See, for positive charge, electric field is here, for negative, it is here. So electric field in the same direction increases. So if electric field is increasing, that is how you are showing equipotential surfaces are closer to each other. Here electric field is less, so there is a distance. Last case, regarding uniform and non-uniform electric field. If you have uniform electric field, then equipotential surfaces are drawn at the same separation. This is D, so this will also be D. Then again D, then again D, like this. And for non-uniform electric field, this separation is D, so this separation for non-uniform electric field. This means electric field is variable right now, and electric field is uniform here, so same separation. Now class, tell me, it's an easy topic, clear to all of you?
Yes, ma'am.
Okay, start writing it. It will take a little time to copy it down, but this is a small topic, but this is important. And equipotential surface will be used a lot in your numericals because work done will be 0. So some hint will be given to you through equipotential surface. Note it down. Wherever you get stuck, ask me. Then we'll start with dipole. Yes, class, those who have joined late. Now, see what we have discussed right now. It's one complete topic we have completed, that is equipotential surface. So I'll not go into the details now. Briefly, I'll tell you what we have discussed. Equipotential surface is basically a surface which has same potential at every point. If you choose this point, you choose this, any point you take there, you will get the same value of potential. That surface, you call it as equipotential surface. And the important point that you should consider is that, see, we discussed this formula, work done is equal to charge into change in potential. Remember, in the last class, we started with this only. Work done and potential for a point, charge for potential due to a sphere. So using this formula only, there are no changes seen in potential. Potential is constant. So change in potential is 0 and charge multiplied to 0 is giving work done as 0 back. One more point that you can remember is that electric field is perpendicular to the equipotential surface. All right, electric field is perpendicular to the equipotential surface. This is also helpful. Rest of the things that you can figure it out while you have written, but this is a small topic, but an important one. Easy. This is very easy. In the question, if some question comes from equipotential surface, there is only one question. What is meant by equipotential surface? Write down the properties of equipotential surface. This is what is asked for. Mention the equipotential surface, what is meant by equipotential surface, and what are all the properties of equipotential surfaces. That is what is asked. So properties you can mention. In short, you can write because lots of properties are there. And otherwise, from numericals perspective, why we are doing this? Why is it important from numericals perspective? Because of the second property which we discussed, that was work done. This property. Suppose the question is given to you and you have to calculate something where work done is required and nothing is given regarding work done. It's just that equipotential surface is mentioned. That's enough. That's a hint to you that if it's an equipotential surface, work done will be 0. If work done is 0, then enumerate whatever is the question that is given. Fine. So this is what you have to remember. Otherwise, please, all those who joined late, please check the initial part, half an hour of the recording, so that you do not miss upon all these. Let us start with the next topic, potential of a dipole. Dipole we discussed in the first lesson. What is meant by dipole? Anyone? Two opposite, yes. See, dipole means opposite charges, not exactly opposite charges, same charges having opposite signs. Same charges having opposite signs. Like, let me show you. Suppose this is a charge plus Q, here charge is there. And you have charge minus. This is a dipole. They are separated by a separation 2A. This is how we discuss. When we get potential due to electric field due to dipole. This is potential due to dipole. When we did electric field due to dipole. Remember that time we had seen two cases, axial and equatorial. Yes. This time what are we deriving? I am deriving this for a general point. Suppose a random point is given. Let's say here I have marked a point. I'm calling this point as P. This point is P. This is a point I have told you. This point is P. A random point I have drawn. What is the separation? This plus Q is separated at one separation from this point P. That, let's say this is R1. Then this point P is separated from this minus Q. Let's say this separation is R2. This separation to this point P. Fine. Now what I'm doing, For the derivation purpose, I'm just passing a line that is passing through the center, means dividing this into A, making this as A, to some angle theta. For the calculation, I am dropping certain perpendiculars. This is just for the derivation purpose, just for the derivation. I have dropped certain perpendiculars. Fine. Now, remember when we did for electric field due to a dipole for axial or equatorial point, we discussed that the separation of this point to the center of dipole, this we take it as R. So here, center of dipole to the point of calculation, this is your R this time. Clear? Let me name this as something. This is P already. Make this as C point, mark this as D point, make this as B, make this as A. All right. A, B, C. This is D. This is point P. This is a center, so let's make it as this figure. You have to remember. Rest of the derivations you will be able to manage using your basic trigonometry. In the derivation also in your exam, remember this diagram. And just remember the initial steps. See, now after drawing this exact diagram, you will be able to start in your exam also well. You'll be able to write it well. So potential at point P when we are calculating. If I want to calculate potential at P, directly I cannot find it out, but just basic what we have studied from last class, at least that we can discuss. If I want to find out potential, that we can discuss. If plus q charge is present and separation is r1 from point of calculation, what is the general formula of a dipole? Not a dipole, potential. Last class we have done this. Plus q is the charge, r1 is the separation. What would be the potential? Yes, Fia. Plus q is the charge, r1 is the separation. What is the potential? You people have revised or not the last class which we discussed? Potential due to a point charge we have studied. Turn your pages at least. Check all of you. If potential due to a point charge we are calculating, charge is given, separation is given. So what is the general formula? Fia, your answer?
KQ by R, sir.
KQ by R. So yes, here
Yes, sir.
that is the general formula. Please do not forget that class. These general formula no, for forces, for electric fields, for potential, these are the basics of your electromagnetism. All right. So yes, KQ by R. So K, what is the charge? Q by the separation, that is R1. And what is this? Is a negative charge. Remember, we have discussed that potential is a scalar quantity. So you'd have to put in the sign. That becomes minus KQ by R. Let's do one thing. Let's take KQ common. So we are left with 1 by R1 minus 1 by R. Now, let me name this as equation 1. This is your entire derivation. That's it. This actually is your entire derivation. Problem is that we can use R. We can use R. Why? Because this is the separation from center to the point of calculation. This is given, this is used. But R1 and R2 are no separations. This I have taken for the derivation purpose. I cannot use R1, R2, AC, or BD. These are just constructions that I have made. So I cannot have R1 and R2 in my answer. I have to replace it. What all things I can have? I can have theta because it is being subtended here. I can have R, I can have A, I can have 2A, I can have plus Q, I can have minus Q, but nothing that I have chosen, right? Now see, please pay attention, class. When we come to this triangle ACO, this triangle, this smaller triangle, ACO. See, if I talk about cos theta, this is theta, so this will also become theta. If I talk about cos theta, This becomes base by hypotenuse. That is CO divided by AO. OC divided by A. So what is OC? OC is actually AO cos theta. Agreed? This is AO cos theta. What is AO? AO is just this half of 2A, that is A. Yes? So your OC, this will become A cos theta. Now one more thing. Look here. Look at this. PA and PC. This looks a little longer, but how much is this longer? Negligible. You can at least say PA is almost equal to PC, almost. Yes, we know that this is a little longer when we overlap it, but how much longer? When we are dropping the perpendicular, this is not so long, right? If I have not drawn the perpendicular well, perpendicular would be like this. So that will be almost equal. If both of them are equal, see, pay attention, this is a little lengthy derivation, but this is a derivation that is repeating, that has been repeating itself every year. So just pay attention. And once you practice this, this will become easier. It's just that we are substituting these values. We don't want R1 and R2 in our calculations. Now pay attention. PA and PC, they almost are equal now. PC and PA. Yes. Now, what is PA made up of? We have to write, not PA. We have to write out what is PC made up of. PC, this entire PC. We can say PA or PC both are equal to, they are made up of this. PA is equal to PC. And
Right, PA plus OC.
PA plus?
OC.
Yes, Fia, what are you asking?
No, ma'am, sir, what is PC is made up of? We can write PO plus OC.
Yes, that is PC. Yes, that's what I'm telling. PC is PO plus OC. That's what I'm telling, the same thing. PA is equal to this because PC is equal to this. Now writing everything, because we don't want PC in our answer. PC is nothing. We want PA because that will only replace R1. What is PA? PA is R1. What is PO? PO is small r. What is OC? We have calculated OC is A cos theta. Do you get it? Now do you people get it? What have we done? We have actually found the final value of, this is A cos theta, R1's value. We have finally got this, the second equation which is needed. This is the first equation. This is the second equation. At least now I have A in my answer. I'll have theta in my answer. I'll have R in my answer. First tell me, is it clear till here to all of you? Then only the next thing is just carbon copy of what we'll do. First tell me, any doubts till now? Hussein, Aliza, Deborah, clear to all of you? Razin, Rajita, clear? Mariam, Fia, clear?
Ma'am, can you explain once again?
Okay. Others also? Aliza?
Yes, ma'am.
Okay, very good. See, once this is clear, then you will be able to now do the entire derivation by yourself. We have found the value of R1. Now what is the next task? To find the value of R2. Now we'll take this triangle this time because we want to involve R2. So OBD triangle, when you try to find out cos theta, again, base is OD and hypotenuse is OB. So your OD is equal to OB cos theta. And so OD is equal to, again, what is OB? OB is also A. Look, this is also A. The way AO was A, OB is also A. So we have, again, OD is equal to A cos theta. Now, similar to this, if PA and PC could be equal, can't we have PB and this PD equal this one and this one. Again, they are separated by a perpendicular. They are almost equal, not exactly equal, that we know. This is a little longer, but almost equal. PD and PB are almost equal. Yes. So what can I write now? How can I write PB? That is PO minus OD. Right, class? PO minus OD. If you from the value PO, if you're subtracting OD, what are we left with? PD, right? And that is equal to PB. So what your PB is ultimately equal to? The PB is ultimately equal to PO minus OD. PB is R2. What is PO? PO is again R minus, and what is OD? A cos theta. This is the value of R2. This is the third equation. So you have R2, you have R1. Put this in the first equation. What was our first equation? KQ 1 by R1 minus 1 by R2. Fine, let us put this. Now your physics is over. It's just that basic mathematics which you all know. KQ 1 by R1, right? R plus A cos theta. Minus 1 by R1, R minus A cos theta. Value of R1 and R2 have been substituted. Now it's difficult to use this formula. Let us simplify using our mathematics. Now you don't have any logic over here. You just have to solve the equations. Let's take the LCM. R minus A cos theta minus R plus A cos theta divided by R plus A cos theta into R minus A cos theta. So potential will be equal to, let us open up the brackets. This becomes R minus A cos theta. This is minus, that becomes minus R minus A cos theta. This is A plus B into A minus B. Remember this identity? A plus B multiplied to A minus B. Can anyone tell me what is the answer equal to? In 8th class, you people have done this identity. A plus B into A minus B.
A square minus B square.
Very good, Fia. A square minus B square. So A plus B into A minus B. That becomes A square minus B square. R minus R will be cancelled. Now see what all things we are left. KQ we are left with a minus sign. This minus sign I'm keeping. And 2A cos theta divided by R square minus A square cos square theta. Can any one of you tell me which quantity is this? Very good, Fia. Dipole moment. Yes, this is dipole moment. This is the dipole moment. Charge multiplied by, see here we are getting Q into 2A. That is dipole moment. All those who are new, this is the formula of dipole moment. You take the charge, multiply by their separation, you get dipole. So what is the formula? Minus, right? We are using the formula minus Kp cos theta divided by R square minus A square cos theta. Let us ignore the minus sign also because it's not a vector quantity, it's a scalar quantity. So if it will be negative, it will automatically become negative. If it is positive charge, it will come. This is without any approximation. Without any approximation means no conditions are given. You will use this formula as it is. Just in case class, if this separation R, no, this separation R, this is very, very, very much greater than this A. Though this is greater, but this is very, very, very much. It's like R is 1000 and A is just 1. So much difference. That is known as ideal dipole approximation. if your R is very much greater than A, so R square will be huge. It's like if R is 1000, this A square, A cos theta, this is 1. When you will square it, R square will become, what will A cos theta become? Still 1. So when you are subtracting this 9, 9, 9, 9, 9, what is this almost equal to? This is again back equal to this, right? Or even 1000 minus 1 is 999. So 999 is approximately equal to 1000. So if this is so huge, we can replace R square minus A square cos theta as almost equal to R square. So the formula becomes Kp cos theta. This is the condition you have to check before solving, whether you have to use the formula without approximation or before approximation. How will you check? You will check by this. Coming to the axial and equatorial line, we didn't discuss it. This is just a general formula. This is a general case of dipole. No axial point, no equatorial point. This type of question we didn't do. This type of derivation we didn't do in electric field. There we had two separate derivations for axial and equatorial. Now what? Now it's just that, see, if it's an axial line and the point is lying on its axis. This is the axis. The point is lying on its axis. So your theta will directly become 0. In this formula, V is equal to Kp cos theta by R square. You will have cos theta as 1, right? Because cos
Kp by
0,
R square.
yes, you will have Kp by R square. So this is the formula for axial line. And if it's equatorial, if it is perpendicular, theta is 90 degree. Can anyone tell me the answer directly?
Ma'am, that is also Kp by R square.
No. What is cos 90?
It's 0, ma'am.
What is cos 90?
0.
0, right? So cos 90 is 0. It means potential is 0 at the equatorial. Is the entire derivation clear to all of you? Write it down. Start writing it down. Take your time. Wherever you get stuck, let me know. I'm here.
It should be 15 minus a square cos square theta, right?
Yes.
Final equation should be kp cos theta divided by r square minus a square cos square theta, right?
Cos square theta. Yes, yes. Cos square theta. Wait.
Ma'am, can you scale up?
Class, just note down the question first because it's a little lengthy question, then we'll practice it. First note it down, then I'll discuss. Let's discuss. I think 5 minutes have been gone. So let us now discuss it. See, two charges are given, minus q plus q on the axis. This is given, but this doesn't change your answer. Remember this type of question we did in the first lesson also, when we started with dipole. So two charges are present, plus q and minus q. They are placed at 0, 0, 0, 0, minus a and 0, 0, plus a. So they are already given. This is drawn in the figure. It is saying potential at point A. Where is point A? 0, 0, z. Okay, at this point, that is 0, 0, z. See, understand this class. First, we have to identify the point. When it is saying 0, 0, z, this is your x coordinate, this is your y coordinate, this is your z coordinate. It means the separation is equal to z. Here your r is equal to z. It means this is lying on its axis somewhere here. This must be 0, 0, z. So potential at this point A, this will be Kp cos theta divided by r square minus a square cos square theta. Fine. What is r? R is given as z. So that is Kp cos theta z square minus a square cos square theta. All right. Now, C class. If the point is lying on this, let's say 0, 0, z, this is somewhere here. This is our A point. From first, this is the first one only. See 0, 0, z is lying on this axis sphere. That is your r is equal to z. So we have substituted z. Now this is the axis. Z, this point A is lying on its axis. It means cos your theta is 0 degree and your cos 0 degree is 1. So this is the axial lines case, right? That is, this becomes Kp by z square minus a square. Without the approximation I'm using. All right, because nothing information is given about r as such. Second point says B is x comma y comma 0. So x comma y comma 0, this is some random point over here, x comma y comma 0. Yes. Now C class, this is somewhere between the plane, xy plane, yes, x, y and z. So this is somewhere here, B point. Can you see this is the plane, xy plane? And what is z-axis? Z-axis is perpendicular to it. It means this point is actually lying on the equatorial line of dipole. So the answer to the second part, VB becomes 0. VC, x comma 0 comma 0. Again, when the point is lying on the x-axis, x, y and z, x comma 0 comma 0. X-axis is also perpendicular to the dipole, z-axis. Dipole is there on the z-axis. If any point is there on z-axis, we will write it as axial line, the way we did in the first part. If any point is there between any planes or any other axis apart from z, that becomes equatorial, right? So VC will also be 0 because of 90 degree. Third, work done in carrying proton from B to C. All right, work done in carrying proton from B to C. C class, we have the potential at B, we have the potential at C. Work done is charge multiplied by change in potential. What is the change in potential? VB minus VC is 0. So work done is 0. It means this is an equipotential surface if there was a surface, but this is a dipole, so nothing. Does work done depend upon potential between B and C? C class. Always remember in such type of questions. Work done is a path independent quantity. Because this I have discussed earlier also in electric charges and field, but electric field, this electric field is conservative. That's fine. It means you have initial point A, you have final point B. You go from A to B like this. You go from A to B like this. You go from A to B like this. Second part, third part. Work done in 1 will be equal to work done in 2 equal to work done in 3. This is actually part of your class 11. Those who have forgotten, work, energy, and power, from there this has been extracted. So it can be related. Not a very simple, easy question we practiced, but if you look at it here, it's just axial and equatorial lines identification. Note down the solution.